Well, hi, thanks for watching. This is part one for the notes for the unit on energy. So as we start this unit, I just want to kind of give you the layout. Studying energy is actually studying lots of different things because pretty much every area of science somehow connects with energy. So if you take a chemistry class, you're going to study chemical energy. If you take a class in biology, you'll study how energy is maybe absorbed by plants from the sun and how it's used then when perhaps animals eat the plants, how that energy gets converted to a form that the animal can use. If you study geology, you'll study the energy associated with perhaps the movement of the tectonic plates on the earth, astronomy, and all sorts of different areas of science all relate to energy. So I think of this as like the great unifying idea in all of science is the idea of energy. So we're going to start, of course, in this class somewhat simply and just kind of set the stage for things that you'll see later on as you study more things both in this class and in classes you'll take after this one. So one of the first things that I think maybe surprised some students, and you may have heard of energy before but not realize that it's something that can be measured with numbers and units, just like let's say you can measure a distance, you can measure a temperature or a volume or a mass. Those have numbers and units as well. So the answer to this first question, can it be measured with numbers, is definitely yes. And when we measure in this class, we're going to use units called joules. It's actually named after a scientist from a couple hundred years ago, James Prescott Joule. And there are other units that you use. You may have heard of calories before. Calories is a unit of energy. It's often used in the food industry. If you're in the heating and air conditioning trade, then you use units called BTUs. So there's lots of different units for energy, but in here we'll stick with joules. And you'll usually see lots of different forms of energy described, but I want to start with the two that we're mostly going to focus on here at the beginning. And both of these forms of energy are going to be considered a mechanical energy. And I'll describe later how the mechanical energy is a different form than some of the energy, other forms of energy. But these are probably the two that you've heard of before. So when we describe mechanical energy, this is the kind of energy that perhaps like you as a person could possess and easily turn into another form. So the first type of mechanical energy that you'll usually hear described is kinetic energy. And if you just think of this as motion, anything that is moving possesses kinetic energy. So let's say, for example, a moving car has kinetic energy, and literally everything that is moving has some amount of kinetic energy. Then there's another form that mechanical energy can take. It's called potential energy. So that word can be a little misleading, but I sometimes like to think of it as something that could eventually turn into kinetic energy. It has the potential to turn into that, is said to have potential energy. And this also can take two forms. The one that we will deal with most in here when we talk about potential energy is known as gravitational potential energy. My abbreviation for this will be GPE, gravitational potential energy. And an example of that is, let's say, a book on a shelf. So why does a book on a shelf possess gravitational potential energy? Well, it's because of its height. Because it's high above, in this case, like a floor, if we were to knock that book off of the shelf, you could see that we would suddenly have some motion, some kinetic energy. And so when we talk in the language of energy, we say, well, where did that kinetic energy come from? Why was it that the book was able to have that? And it's because it at one time possessed gravitational potential energy because of its being high up on the shelf. And there's another form of potential energy that's usually referred to as elastic potential energy. So elastic potential energy is not because of any height, but because of sort of a stretchiness. So if you've ever taken a rubber band between your fingers and kind of stretched it out and pointed it at somebody, you know that they have this sense of, they get a little nervous, little flinch perhaps. And that's because that potential energy that you've stored by stretching the rubber band could certainly turn into kinetic energy just by pulling your finger out of the way and watching it fly. There's also a spring. If you squish a spring, or if you stretch a spring, you certainly see that there's the potential for something to start moving. So, you know, spring-loaded launchers of some kind, those are a way of storing potential energy so that we can turn something into motion later. You might think up here another way to describe potential energy as stored energy. Okay, so these are some categories. Again, you've probably heard of these before, and I just kind of want to show you how they all relate together. We will deal mostly with the GPE and the kinetic energy. We will abbreviate that KE when we do our work with numbers. And you'll see there's other forms as well that we describe. We'll get into those in just a little bit. So as we go to this next page, now I'm going to show you how we start tying the numbers in to the calculation for both kinetic energy and gravitational potential energy. So in both situations here, I'm going to describe what we call a formula or a math equation that we can use to get to what the value of the energy would be. I'm not going to prove like where these came from. For now, we're just going to leave it that that these are the correct ones. Maybe in a future class, like in a physics class, you can get into why these equations are what they are. For now, I just want you to be able to use them. So for kinetic energy, the formula is written this way: 1/2 mv squared. So we'll go through each part of this. Now, obviously, the 1/2, that's just the number. M is a symbol that stands for mass. And in physics, which is kind of what we're studying here, when we measure mass, we're going to measure in kilograms. And that's because I want my units of energy to come out in joules. And if we want joules, everything has to be measured in kilograms. Kilograms is a convenient unit to use for big objects, things like cars and people. But in maybe a smaller scale, you might have something measured in grams, and you would need to turn it into kilograms through a conversion. And we'll talk through that when it's time. So what does the V stand for? It seems a little odd that we would use V for this, but I want you to think of that V as an abbreviation for speed. It might seem more logical to use the letter S, but we tend to not use the letter S in symbols like this because it just looks too much like the number 5. So V is actually usually translated as velocity. And in our understanding so far, speed and velocity you can think of as pretty much interchangeable. And what do we measure speed in? Well, if we want our energy units to come out in joules, we need our speed units to be in meters per second. You're probably familiar with the units for a speedometer in a car, which are in miles per hour. It's always some distance unit divided by or over some time unit. So in this case, meters and seconds are the units that we use for the distance and the time. So let's look at an example here. We have a 3,000 kilogram car moving at 6 meters per second. Let's find out how many joules of kinetic energy that is. So when we do math problems like this in here, you always show 3 steps. The first step being simply writing the symbolic equation that we have here. So we would start with KE equals 1/2 mv squared. Now there is an understood multiplication here. I imagine you've seen in math class. If you don't put a math operation in between 2 symbols, it just means you're going to multiply them together. So this is 3 things multiplied together. And then we would write in the next step the substituted values for each of those symbols. Now the 1/2 is not really a symbol, it's just the number. but we would write the mass. Now that I'm putting numbers in, I really need to put a time sign in, something like a dot, or you could use the X. You could even use parentheses, as they probably have shown you in math class. But we would always want to put in whatever symbol is next in our symbolic equation. So this is M, and so we would go and we get the mass, which is 3,000 kilograms. And then we would multiply that by v squared. Well, v is the speed. In this case, here it is in meters per second, 6 meters per second. But notice that that number is squared. Now, it's common for some students to think of this as multiplying by 2, but that is not what squaring means. Squaring means like multiplying by the speed a second time. But we don't usually write it that way, but it means, in this case, like 6 times 6. Now we would take a calculator. If you don't have a calculator nearby, in my classroom you can always borrow one. And we would just multiply 1/2 times 3,000 times 6 squared, or you could also write 6 times 6, or you could simply put in 36 into the calculator. And this will give you a result of 54,000. Sounds like a really huge number, but when we're talking about big cars moving at kind of normal speeds, we're definitely up in the tens or hundreds of thousands. So the kinetic energy, I like to put a box around my final answer, would be 54,000 joules. Okay, now a mistake that sometimes gets made on a calculator is some people will put the square in at the wrong time. If you multiply the 1/2 times the 3,000 times the 6 and then square it, you're going to get like 8 million or 81 million. And that's not what you want to do. You want to make sure that the only number that gets squared in the equation is the speed. Okay? Now, a couple of the things I'm going to ask you about as you start dealing more with these equations is about how changing one value in the equation will change the kinetic energy. So I'll give you an example here. What if instead of a 3,000 kilogram car, we double that to a 6,000 kilogram car? If it was still moving at the same speed, what effect would that have? And what I want you to imagine here, or you could actually do this on your calculator, is putting a number that's twice as big into a multiplication problem gives you a product or a result that's twice as big. So doubling the mass will also double the kinetic energy. However, doubling the speed will not have the same effect, and that's because the speed gets multiplied 2 times in this because of that square. So if I were to change this from a 6 meter per second up to 12 meters per second, it's not going to double the kinetic energy. It would double or quadruple the kinetic energy. And again, you can try this yourself. If you put in 1/2 times 3,000 times 12 squared, instead of 54,000, you're going to get, would that be about 216,000? Doing some math in my head here. I better check that. Yeah, 216,000 is 4 times as much as what you had before. So one of the things to see here is if you could change one thing about your two values here, the one that would have the biggest effect on the kinetic energy is changing the speed, because that gets squared. So I call those proportion kinds of questions. Good way to start thinking through things. Now let's do a similar thing for gravitational potential energy. I'm going to give you the symbolic equation. It also has an m in it. And then it has 2 other factors that are all multiplied together, m times g times h. So we just have to know what these 3 stand for. And again, the m, just like it was for kinetic energy, is the mass. And that has to be measured in kilograms. G is a symbol for, now this goes by a couple names, and I like to think of it as probably the best name is the strength of gravity. I didn't give quite enough room on this line here. But the strength of gravity describes how strong the gravitational field of the Earth is, wherever you happen to be. Now, this would also work if you were to go to the moon, for example, but the strength of gravity on the moon is a lot smaller. And so when we're on Earth's surface, we're going to use 9.8 as the number. And now you'll see this written differently in different places, but when I like to describe the strength of gravity on, let's say, the surface of a planet or something, I like to use the units of newtons per kilogram. Now, these are probably not units that are familiar to you, but for now, you can just assume as long as we put them in these units, that we will get joules of energy out when we do our final calculation. I'm going to explain why the gravity is important here, but let's get to the last symbol. H is a symbol for height. And if you remember, back on the first page here, I described something having gravitational potential energy as something that has some height, because it has the ability to perhaps fall off of that high location and turn the stored gravitational potential energy into something moving, which would have kinetic energy. And we want to make sure we measure the height in meters. We'll use the symbol m for meters. You've got to be careful here, because the symbol m for meters is the same m that we're using for mass. You want to be careful you don't confuse those things. So now let's take our 3,000 kilogram car, and now it's sitting at the top of a cliff. So you might picture, oh gosh, what would happen if this thing fell off the cliff? We'd get some kinetic energy out of it. But when it's at the top of the cliff, we've simply stored the energy in potential form. So like we did before, and like I always expect you to do, write the symbolic equation just like that, mgh. Then you start putting in the three values. Put in the mass first, then the g, then the h. Don't mix up the order when you put your numbers in, because I will get kind of confused wondering whether you really know what the mass and the g and the h stand for. So the mass here is 3,000 kilograms. I'll put a little dot because this is all multiplication. As long as we're on the surface of the Earth, or very near the surface of the Earth, we can always use 9.8 for the value of little g. And that's in newtons per kilogram. And then we multiply by the height. The height above the lowest surface, so that would be the height of the cliff, or 20 meters. See how I put units on all the numbers? Just be careful here, because sometimes you'll have a mass given in grams, and you're going to have to figure out how many kilograms that is. So you got kilograms, you got newtons per kilogram, and you got meters. And then the calculator will take care of the rest. 3,000 times 9.8 times 20 gives you 588,000 joules. That's a lot of energy. A lot more than the car that we had on the previous page. It was moving at 6 meters per second. So don't be too afraid of seeing these huge numbers like this. This is very typical when we're measuring things in kilograms. We've got things as high as 20 meters. That's several stories high. So we're going to get these big numbers, and just don't be bothered by that. That's why we have calculators. You can check your work with those. Okay? So if you need to stop here and look back, how to calculate those two things, how you show your work in 3 steps. This is step 1, step 2, step 3. I'm going to have you do this when you do your own practice, so make sure you got that down well. And then we'll go on to the next page. So now we're going to describe some other forms that energy can take. And back on page 1, you remember I described the forms known as mechanical energy. But there are 5 other common forms, and even more than that. But this textbook and in this class will kind of focus on these total of 6. So we're going to make a table of those here, and I'll start with the one that we've already described. And that's what we call the mechanical energy. Those are the ones that I just did examples of with kinetic energy and potential energy. So when we talk about something's mechanical energy, we talk about the sum of its kinetic energy plus any potential energy. And remember, potential energy can also take 2 forms. There's the gravitational potential energy, like what we calculated with the car on the cliff, But there's also a way to calculate how much elastic potential energy something has if you were to pull a spring or stretch a rubber band, but we're not going to get into that in this class. So the sum of these two energies in all its form would be what we call the mechanical energy. So, you know, when we have a moving car or the book on the shelf or a stretched rubber band, all of those are different forms of mechanical energy. Okay, so what are some other forms? Well, thermal energy is a second form. And this is interesting because everything you will ever encounter has some amount of thermal energy. It's associated with the microscopic vibrations or movements of the small particles in an object or in something. So even though you can't see them, every particle is always in motion. And you remember this when we studied the states of matter. Very first unit that we studied this year, we talked about how there are low energy states and there are higher energy states. And those lower energy states are what we usually call solids. And then when we get a lot of motion of the particles, we go up to liquids and then finally to gases, and we could even go beyond that. But even in the very lowest energy state, we still have some very small vibrations of the particles that make up a solid. You could never see it, but all of that energy of all of those particles added together is what we refer to as the thermal energy. Okay, so it's kind of funny to use this as an example, but everything has thermal energy. And we tend to think of things that are hot as having a lot of thermal energy. So that's simply because those particles in that object have acquired some energy and are moving more rapidly, and there's more of them moving than in something else. But there's nothing we'll be able to think of that doesn't have some thermal energy. All right, a third form is what we call chemical energy. This is actually also something that we studied back in the first semester when we were studying chemical reactions and chemical bonds. And not everybody got into this as much as others, but chemical reactions are all about energy. When we have an explosion, it's because of a chemical reaction, or things that get hot or things that get cold, it's because of the chemical energy that are stored in the chemical bonds. And perhaps when those bonds are broken, we have to put some energy in to break the bonds. So we'll describe the chemical energy as stored in the chemical bonds of compounds and that's probably enough to maybe start here, but if you think of forms of fuel, these are all forms of chemical energy. So coal and gas, those are forms of chemical energy. You can also have little storage devices known as batteries. That's a way of storing chemical energy. Another form of fuel is wood. You know, you can burn wood, and once you start those reactions happening, when those chemical bonds are broken and reformed as we burn the wood and turn it into basically ash, then we release a tremendous amount of the energy, and that's where we get the energy from wood when we burn it. The next form of energy, you'll recognize this one. is called electrical energy. And you would just know it as electricity. In fact, I'm going to use that as my example because that's really what most people call it. So you know electricity, maybe you've just not thought of it this way before, as it's a way of moving energy from one place to another. So we actually have some energy maybe stored in a battery somewhere, and we'd like to get something moving. And so we can use electricity to take that energy that was stored as chemical energy in a battery and to move it somewhere else so that we can perhaps make a light bulb glow or make our computer run or our TV run. And so that's what we call electricity. But what's actually happening is this is the motion of electrons through conductors. Well, you know what electrons are. And if you remember when we talked about different kinds of elements, some were considered metals. And those metals have electrons far from the nucleus that are very, very weakly held, and so they're very easy to move. And in metals, there's so many of these that those electrons are so free to move that it doesn't take a whole lot to get them to move completely from one atom to the next and to the next, all the way down the metal. We call those conductors or metals. And so when those electrons are moving, we refer to it as electrical energy or electricity. So again, not anything that you're not familiar with. All right, what's our other two forms? Well, you got to be careful for this one because it's often confused for electrical energy. And this is kind of a fancy $10,000 sciencey word, electromagnetic. Electromagnetic energy is energy that moves in the form of waves. And it's kind of unique because it's the one form of energy that we have among all of these that can move through space. Now, it doesn't only move through space, but everything else on our list here requires some kind of stuff, some matter, some mass. So we have to have like little particles in order to have thermal energy. We have to have atoms in order to have chemical energy. We need electrons to have electricity. But electromagnetic energy can move through space, which means nothingness. And so you'll know this by a more common name. So light, you know, that energy that comes from the sun through space and warms up the earth and illuminates the earth, well, that is electromagnetic energy as it moves through space in the form of waves. So there's light, and there's other forms. So when we have cell phones and the way they communicate and send information through the space, through the air, that's actually considered radio waves. There's X-rays from space. And there's other forms as well. So you may have heard of microwaves or gamma radiation, or I'll put this one in because you probably heard of this, UV radiation or ultraviolet. That's short for ultraviolet. Those are all different forms of electromagnetic energy. And all of these forms, in fact, every one of those is something that's traveling from the sun through space. And every star gives off different forms of electromagnetic radiation. And that travels through space, and a lot of it reaches us here on Earth. It's how we know a lot about what's out in space, is based on the electromagnetic energy that we receive from it. And what's our last one? This one is probably not as familiar to you, although it's a very important source of energy and could potentially, if we figure out a safe way to do it, cause some of the energy crisis we have with not having enough energy to fuel the needs of the world. But the nuclear energy, this is associated with the energy in the nucleus. So now we're talking about atoms again. I want to distinguish this from chemical energy. Chemical energy had nothing really to do with the nucleus. It was in the bonds, which are the electrons, kind of pulling one atom towards another, but it all has to do with the electrons. Now we're talking about something going inside the nucleus. And this can be stored or released through smashing nuclei together. We call that a nuclear reaction, where we take two atoms, we actually smash them together, and we form an entirely new element, an entirely new atom. That's not the same thing as just bonding a couple of atoms, getting them close to each other, and having them hold on to each other. This is entirely different. And so a tremendous amount of energy is stored inside these nuclei, and if we can safely harness that, release it in a controlled way, this is what we do in a nuclear power plant, then we could really exploit this. But the problem is, if it gets a little out of control, sometimes these the nuclear reactions go out of control, and then you've got big problems, huge releases of energy, and you may have heard horror stories about things that happened in places like Chernobyl in Russia back in, I think, the 90s, 3 Mile Island here in the United States. So here's two words that you'll hear when we talk about nuclear energy. Two nuclear processes, one known as fission, that's where you take a nucleus and you split it apart, and the other called fusion. Fusion is where you take nuclei and you smash them together. And in each of these, we can store or release these vast amounts of energy. Okay, so gosh, we're just past a half an hour here, and hopefully this wasn't too bad if you could break it up, but there's a lot of information in here, but this is all kind of the groundwork for what we're going to be talking about in this unit and in several units beyond. So when you get all this down, if you need to, go back and replay part of this, and then I'll take a look at it, make sure you got everything good, and then we'll go from there. All right, thanks for watching.